All right, so in this video, we're going to be looking at the independent t-test and doing an example by hand of this. And so for the independent t-test, we know that we're going to be comparing two different groups. It's also important to know that the independent t-test has a bit of a lengthier process when we're doing it by hand, but we're just going to take it step by step as we have with the other procedures. And so in this example, we're looking at some scores for how patients are doing post-surgery. And so particularly we're comparing two groups, one that has had surgery less than 6 months ago and one that's had surgery more than 6 months ago. And these patients have filled out questionnaires which give them a score of 0 to 20 for how well they're doing and progressing with their recovery. And so I'm just going to put our scores over here. And so we have our less than 6 months group here and our more than 6 months group here. And we have 4 patients in our less than 6 months group. And their scores are 7, 12, 10, and 10. And in our more than 6 months group, we have 5 patients. We know that in the procedure that we've learned for the independent t-test, we don't have to have an equal number of participants, so this is just fine. And so our scores here are 18, 16, 16, 17, and 14. And again, from just looking at our scores initially, we can say that these do look like they might be different, but the key here with hypothesis testing is to see how different are they? Are they different enough that statistically significantly different enough that we can say that this is unlikely to be due to chance. And so we're going to start off, just like always, with writing down our research and our null hypotheses and frame those in terms of our populations. And so for our research hypothesis, one version of how we could word this here is going to be that patients who had surgery less than 6 months ago will have different scores or will score differently than patients who had surgery more than 6 months ago. And again, for the purposes of determining whether we have a directional or a non-directional hypothesis, here we have some mores and lesses here, but here I see that less than 6 months ago, more than 6 months ago. This has to do with my groups, not the comparison that I'm making between those groups. And so the main word here that I want to pay attention to is how do those groups compare? We're predicting here that they will score differently. I don't have a direction here for whether I think one group, our 6 month group, will be greater or less than the other. We might have an idea here that we expect people to be doing better the longer that they are after surgery, but we're not sure here. In this case, we're predicting just that they are going to be different. Oops, before we get to step 2 here, let me write out my null hypothesis. And so our null hypothesis we know is just going to negate this hypothesis. We're just going to say in this case that patients who had surgery less than 6 months ago will not score differently than patients who had surgery more than 6 months ago. Again, the key word here is that they will not score differently. And so this would mean that my groups are the same and that my results would not be significant. And you can imagine we don't have a whole lot of information in this example, so there might be lots of other factors that are impacting whether these results will be significant. And also, with this idea of that this will be different versus more or less. So perhaps the type of surgery, the health of the patients beforehand, we can imagine that there's some more specific information that's influencing this hypothesis. And so moving on to step 2 here, I'm going to start this over on this side of my page here. And so for step 2, we know that we need to get our comparison distribution information. And this is a lengthy step in the independent t-test. And so we're going to, again, go step by step here. And so the first thing that we're going to do is we're going to get our degrees of freedom. And in the independent t-test, we have 3 different types of degrees of freedom that we need to get. We need to get the degrees of freedom for our first group, for our second group, and then our total degrees of freedom. And our typical degrees of freedom formula is n-1. And so in this case, we're going to have the n of group 1 minus 1, and for our first group's degrees of freedom, and n2 minus 1 for our second group's degrees of freedom. And then for our DF total, we're going to have our degrees of freedom from group 1 plus our degrees of freedom from group 2. And so we said we had 4 patients in group 1, 5 for group 2. And to get the DF total, we're going to add DF1 plus DF2. Finish out this calculation here. And so now we have DF1, DF2, and our DF total. And so the next thing that we want to do is we want to get the mean of each of our groups. And so we remember that our formula for the mean, which we always want to include in our calculations, we have the sum of x, and that sum divided by n. And so we're going to get the mean of group 1 and the mean of group 2. And so again, we have our scores here, 7, 12, 10, and 10. If we add those up, we will get 39. And divide that by n. So there were 4 people in this group. And so that gives us 9.75. The mean of our second group, we have 18, 16, 16, 17, and 14. And if we add those up, we're going to get 81. We said there were 5 people in this group, so dividing by 5, and we're going to get 16.20. And so the next thing that we need to do is we're going to just note the mean of our comparison distribution. And so here, this is going to be the mean of our distribution of differences between means. And that's going to be 0. And this is, we assume the comparison distribution mean is 0. And again, this comparison distribution is the distribution assuming that our null hypothesis is correct. I'm going to grab a second sheet of paper here. We're going to continue on by getting an estimated population variance for each of our groups. And so we remember that our formula for our estimated population variance is going to be the sum of x minus m squared divided by n minus 1. So we're going to get an estimated population variance for each of our groups in this case. And so for group 1, we're going to take our raw scores. So we have 7, 12, 10, and 10 again. We're going to subtract the mean of our group, which we already calculated, and we said was 9.75. I'm just going to set this up here. I'm going to start off by subtracting that 9.75 then from each of these scores. And so as I do that, we have 7 minus 9.75, and that's going to give us a negative 2.75. 12 minus 9.75 is going to give us 2.25, and 10 minus 9.75 is going to be 0.25, and the same thing here. So I can just write that again. And now we're going to square each of these scores. And so negative 2.75, and again, remembering that we have to make sure that we're using our negatives correctly with our calculator. So some calculators might require you to use parentheses or something else. Remember that when we're squaring a negative, we're always going to get a positive. And so if you haven't, something has gone wrong. And so you can take a moment to try to correct that, or you can just do this without the negative sign, since it will be this negative 2.75 and 2.75 squared will each be the same thing. So when I do that, I'm going to get 7.5625. And again, we want to round our final answers always to 2 decimal places. If there's only a couple of decimal places, if there's only 3 or 4 on a calculation like this, sometimes I will go ahead and just use up to that 3 or 4 decimal places. I wouldn't recommend using beyond that. And we want to be a little more careful than I have here about making sure of which number that goes to, or so we make sure that we've calculated all of our numbers here. The next up, 2.25, we get n squared, we get 5.0625, and 0.25 squared, we get 0.0625. And again, we have that calculation twice. And so next up, I'm going to add these together. So I have these 4 numbers that I'm going to add together right now. And as I calculate that, I'm going to get 12.75. And then I divide by n minus 1. So divided by 4 minus 1, 4.75 divided by 3. And finally, I get 4.25. And so again, this is my S squared of my estimated population variance for group 1. And so I'm going to get my estimated population variance for group 2. And so we're going to do this entire process again, just with our second set of numbers here. And step D, because we want to get both of those estimated population variances before we move on to the next step, when we'll need both of those. And so S squared 2. And so we have 18, 16, 16, 17, and 14. And our mean there was 16.20. And so just as we did up here, we want to subtract the mean from each of these raw scores, square it, add those those square values together, and then divide by n minus 1. And so here 18 minus 16.2 is 1.8. Then we have negative 0.2, negative 0.2, 0.8, and negative 2.2. And as I square each of those, I'm going to get 3.24, 0.04, and the same thing here, 0.64, and 4.84. And again, when I'm doing this by hand, I like to try to line all my decimal points up, trying to make sure that everything is as neat as possible so I don't misadd anything as I'm going down my rows here. And so as I add this up, I'm going to get 8.8. And we're dividing by n minus 1, which we said was here was 5 minus 1, which is 4. And then that gives me 2.20. And again, this is for my second group. And so our next step is going to be to get the pooled variance. And so this essentially is going to be this weighted average between my two groups. And so we're going to use our degrees of freedom that we calculated here to essentially get a ratio in order to weight those estimated population variances. And so we want to go back to our DF1, DF2, and DF total. And so DF1 we said was 3, DF total we said was 7, and DF2 we said was 4. And then I have my estimated population variance for group 1, which I calculated up here. I said was 4.25. And for group 2, which we said was 2.20. Once again, we're always making sure that we're really carefully matching these symbols. So if I have an S, I want to sub in for an S. If I have an S squared, I want to sub in for an S squared, and so on. So as we're calculating this, the first thing that I want to do is I want to divide 3 by 7. And so we're going to round this. We want to round to at least 2 decimal places. So I'm just going to do 2 decimal places here. Always 2 at the end. I would say 2 to 4 if you're in the middle of the problem. And that's just to make it a little easier, a little more streamlined here. Make sure I'm copying this over correctly. And so I have 0.43 times 4.25. So that's going to give me 1.8275. So I'll just round to 1.83 here. And then over here we have 1.25. And so if I add those together, we're going to get 3.08. And so again, this is my pooled variance here. Our next step is going to use that pooled variance that we just calculated. And here we're going to get some information here for those distribution of means here. And we're going to get 2 of these. So we can see, I like to almost think of this like we're playing hopscotch a little bit. And so we can see that we had to get 2 estimated population variances. So those are here. 1 pooled variance. We're going to have 2 calculations for this next step, and 1 to get our S squared difference. And then we're going to actually get 1 more to get our S difference. And this is really the process of what this looks like. So I just like to use this to remember kind of exactly when I have to do 2 calculations, 1 for each group, and when we're doing a combination, combined calculation for our groups together. And so here we're moving on to step F. And our formula for this, and again, we're going to do the same thing, 1 for each group. And the reason we do this 1 for each group is because we're divided by n. And again, sometimes when we're doing this calculation, we're going to have different size groups, and so that n is going to be different. And so here we're going to really just plug in what we had here and our ends of each group. And so here we have 3.08, and we had 4 people in that group. And here we're going to have 3.08, and we had 5 people in this group. And so if I want to do that calculation, I'm going to get 0.77 here. And I'm going to get 0.616 or 0.62 if I round it over here. And so the next step is going to be the S-squared difference. And for this, we're going to add together these two numbers that we just calculated in this last step. And so if I have 0.77 plus 0.62, it's going to give me 1.39. And last step, and again, this is all step 2 here of our hypothesis testing procedure. But our last sub-step here is going to be to get S difference. And so to do that, we're going to get the square root of our S-squared difference. And so again, this is going to be a standard deviation that we're using, getting the square root of our variance here. And so the square root of 1.39, we have 1.178, and we'll round that to 1.18. And so step 3, we're going to get our cutoff scores for this test. And so if we go back to our original research hypothesis, we can see that here we predicted that these groups will score differently. And so we had a non-directional hypothesis. And so we're going to have a two-tailed test. And here we're going to be using that 0.05 significance level. And here we need to use, in order to look up our cutoff score in our t-table, we're going to be using our total degrees of freedom, which we calculated as being 7. And from there, we're going to find that our cutoff score is going to be 2.365. And because it's two-tailed, that's going to be plus n minus. So step 4. Step 4 here, we're going to get our sample score. What is our sample t-score for these two groups? And so in order to do that, make this a little bit clearer here, we're going to use mean 1 minus mean 2. And we're going to divide that by our comparison distribution standard deviation. And so we can go back to our earlier calculations of what was mean 1 and mean 2. And we found that mean 1 was 9.75 and mean 2 was 16.2. And this difference we calculated just up here. And so we have 1.18. And so we can go ahead and do the subtraction. And we'll get negative 6.45 divide by 1.18. And we're going to get negative 5.466 or negative 5.47 once we round that. And so this is going to be our sample score. And so our very last step of our hypothesis testing procedure here is going to be to make our decision about whether we're rejecting or failing to reject our null hypothesis here. And so again, typically I like to be able to visualize this, so I could draw out a distribution. I can draw a number line here. I'm just going to draw a number line here. I can try to be as even as possible here. But the important thing here is that I can just visualize this. These are in the right order. And so we said our cutoff scores are going to be plus and minus 2.365. I could say a little to the side, about between 2 and 3, a little closer to the 2. And I know that between 2 and 3, a little closer to 2. And I know that these are then my cutoff scores. We know that, kind of angled these out this way so that we can remember that our sample score needs to be greater than our cutoff scores, than one of our cutoff scores, in order for us to reject that null hypothesis. And so these are the regions out closer, more extreme than our cutoff scores, closer, further out into the tails. That's what we're looking for. And our sample t-score here is minus 5.47. And so this is all the way over here. Actually, I haven't even moved this long enough. We're kind of off the chart here. I can extend this a little more. And so this is my sample t-score. Then we're going to be able to reject our null hypothesis, and we can say that our results are statistically significant.